Good afternoon. I'm Geerd-Dietger Hoffmann, and I wrote this paper with Verena Majuntke from HTW Berlin. It's about the Green Metrics tool, a piece of software we developed to enable good measurements for a varied amount of metrics of software. So we all know that software impacts environmental sustainability, IT infrastructure. I don't have to talk about that. AI technology will increase the demand of resources in general. And what we found sort of 2 years ago when we started this project is that there's not really any good software out there to measure the resource usage. And we said, so you have to start with accurate measurements before you can start optimizing. So the objectives for this talk and for the paper are that even in scientific papers, measurements are not done correctly. I'm not going to point any fingers, but getting good measurements is very hard, and I see a lot of papers where there are lots of aspects are not thought about. It's important to not only talk about energy. All people sort of seem to default on energy because it's the easiest, but there are loads of different metrics. I want to talk about these. I want to present the Green Metrics tool. That's our software tool that hopefully solves a few of these issues. And I want to highlight a few of the features, what we feel is important in getting good resource metrics or resource readings. So there are loads of tools out there that already try to do this. There's Greenframe, Kepler, Scaphandra, just to name a few. But most tools are sort of on logging and not on benchmarking. So there's some scientific work on there in the early days for like embedded devices and stuff, but there's not a lot of tools out there that give you a complete picture of all the resources used that your software uses in a realistic context. So the Green Metrics tool tries to bridge this gap in doing software lifecycle analysis and really trying to get the whole picture shown. So as I already said, electricity usage is the most obvious. Often I see that only CPU power is used, REPL, because it's simple to use, it's just there. But what about the other components, right? We have all these other, we have disk, we have memory, we have all these other usages. Now people are starting to talk, especially in the data center context, are starting to talk about water, heat, material wear, right? You can't use a disk as like for infinitive. You have to, every write incurs a sort of cost on the hardware. And people are now starting to talk about this and sort of think about this. And I think it gives a false picture to only talk about CPU energy usage, because you can write algorithms that, and we've seen this actually, that people have offloaded stuff onto memory, onto disk to save basically CPU usage. But when we look at the whole carbon footprint of the whole problem, it's actually worse. So you have to look at runtime and repeatability. The challenging things in measuring software is like we measure on a huge variety of different setups and different components. So what we saw is that in a lot of readings, you'd have these outliners, and that was the operating system or some other component of the operating system coming in. So we developed NOP Linux, which is like a special flavor of Ubuntu that strips away most of the interrupts. Something I see in a lot of even scientific work is that the state of the machine needs to be the same. So if you do a repeat run 20 times, the first runs are going to use less energy or less resources because the machine is cold. So you really have to make sure that you take all the components and all the settings into consideration. And software is very, very complex nowadays. If you look at software out there that's been run in industry, it's really, you have 200 microservices at some stage. And REPL, which is mostly used, is only on a chip or CPU or core level, depending on Intel or AMD. How do you split this up? You can do it if you fix CPU scaling and you can sort of, you disable high performance threading or hyper threading and stuff, but it's very, very complex. And software is not always straightforward. For example, network traffic is something that lots of people, if they measure software, don't consider. That if they do the same measurements at 3 o'clock at night, your software will use far less energy than if you do it at 12 o'clock midday, because just the network is freer and you have this timing scale. So the Green Metrics tool tries to abstract all this away and sort of gives you an out-of-the-box solution that you can do good measurements. It's based on industry standards, so we use Docker, so you don't have to create a special setup, you don't have to create a special, you can just use your standard industry compose files, which is very important if you go into industry. They don't want this overhead. The Green Metrics tool has a very low overhead, which is also very important, which I don't see reported in a lot of papers, is what's the actual overhead of the measurement setup. So we do extensive analysis to make sure that it's very low, and actually in each measurement say what the overhead was. Also, something we find very important is the comparison between different runs. So once you have good measurements, you want to start optimizing. It's very important that you can compare different runs. And because getting good runs on your desktop machine or even on a server is very, very difficult, you need specialized hardware. You have to fix the CPU clock speeds. You have to disable loads of things in the CPU. So we started a development, a measurement cluster where you can submit a job, you just give it a GitHub repo, and it will do all the measurements for you in a repeatable and with loads of specialized hardware to get the best reading. And we offer optimizations. This is early on, and we're currently working on this. So we look at, for example, over provisioning. So if your Docker container is too large, we say, look, you're not using all the resources. You want to scale down your container. How does it work? So we've got the Green Metrics tool core, which has the system runner, the front end, the optimization, and the API. This takes Docker files, Kubernetes files, some industry standard way of orchestrating software, and then orchestrates Docker containers to run a sort of benchmark. That's called the flow. This can be anything, a shell script, Puppeteer, Selenium are sort of the biggest. And then we have these metrics reporters, which is a wide variety of different types of metrics reporters. And that then basically feeds back into the API. And then from that, after post-processing, we do the optimization, or we do the optimization recommendations. So we sort of wanted to look at the whole software lifecycle. So what we see is that if you look at how measurements are often done, they're not done in a proper way now, apparently. So you don't look at the baseline, you don't look at the installation cost, at the boot up cost. Most software measurements are just done on runtime. And what we see in industry is, especially in CI/CD jobs or something, that the build cost, for example, sometimes is more than the runtime. So you really have to look at the whole software picture. You really have to look at the whole framework that's used and not just the runtime. Next slide. So here's a screenshot of how this looks. So this is a compare view. So we've changed a little bit of code, and you can see the machine energy, which we get through the MCP reporter, the network transmission energy, container energy, and all the different containers. And you see basically from the two commits, there's a 0.61% machine power variation. And then you can sort of do a deep dive into what this is. Here you can see the different phases, which we find very important, that you sort of have the baseline measurement, you have the installation, boot, ideal runtime, and then the different things that are done in your flow. Whereas the runtime here is the aggregate of all the different steps you do. Okay. Here's you can basically, very easy to do good measurements. You just add, we've got this front end, you can just add your GitHub or your GitLab URL. Thank you very much.
Cool. Great, thank you. Maybe just one question for time, and people can ask more on Slack if needed. I don't know if we have a question in the room. Yeah, here. Oh, wait, I'll just move with the microphone.
Hopefully I'll be quick. Thank you very much. Just wondering, your tool, does it work on various OS and chips, CPU chips, or is it specific?
We do. So we've developed on Linux, right? Because Linux enables us to have this like specialized hardware, where we have the NOP Linux operating system interacting with the hardware. We can run under Windows with the Windows subsystem for Linux. But we can't modify the operating system well enough to get good readings here. Mac, you can run on Mac. The problem is that Mac has the power metrics program that basically gives you the energy values. It doesn't have like REPL or something. And it's very hard to orchestrate on Mac. And also the operating system is very bulky. So you can, but to get good readings, we always say use a development, use a cluster, use a specialized machine to get good repeatable readings.
Quick question, just one word. Does it work with ARM chips or
Yes,
not?
yes, yeah, of course, yeah.